This video will give examples with common logarithms. Evaluate log base 3, 10. We can't do this by hand, so what we have to do is use a calculator. But our calculator can only work with common logs and natural logs, meaning that we have to convert this expression into something that has log base 10 or log base e. We can write this using the change of base rule as log base 10, 10 divided by log base 10, 3. Or if we wanted, we could also do ln of 10 over ln of 3. Either way, we can enter either of these expressions into the calculator and we'll find that our expression is about 2.096. Evaluate. Log 1/2 plus log 2/3 plus log 3/4 all the way down until log 99 over 100. The key to doing this problem is to remember our product rule that we learned about earlier. So what we can do with this is rewrite it as 1/2 times 2/3 times 3/4 all the way down until 99 over 100. So now we see that things will cancel out, leaving us with only the 1 in the beginning and the over 100 at the very end. So that is just equal to the log of 1 over 100. Now since this is base 10, what we can do is rewrite this as 10 to the negative 2, giving us our answer as just negative 2. Solve. 2 to the a plus 3 equals 34. I'm going to take the log of both sides of this equation, and then using the power rule we can bring down a plus 3 and multiply it by log of 2. So now we have that a plus 3 equals log 34 over log 2. At this point, we can plug in the right side of this equation into a calculator to get about 5.087. Now to find a, all we have to do is subtract 3, so a equals 2.087. Solve. 5 to the b minus 1 is greater than or equal to 10 to the 6 minus b. So again, I'm going to take the common log of both sides. So log b minus 1 again, I'm going to use the power rule to bring down the exponents. And with the right-hand side, we can use the inverse property of logarithms to see that it's just 6 minus b. At this point, we can enter log 5 into our calculator so that we have b minus 1 times 0.7, just about, is greater than or equal to 6 minus b. Now we can distribute this 0.7b minus 0.7 is greater than or equal to 6 minus b. 1.7b is greater than or equal to 6.7. So b is greater than or equal to 6.7 divided by 1.7, or 3.94. Given that log 2 equals about 0.301, find the number of digits in 5 to the 54th. This is a pretty tricky problem, and it requires noticing that the number of digits in any number is equal to the log of that number. So essentially the number that we're looking for is the log of 5 to the 44th. So we can rewrite this as 44 times log 5, and then, knowing that 5 is equal to 10 over 2, we can replace this expression, and we can have log 10 minus log 2, all using properties of logarithms. So that equals 44 times, we know that log of 10 is 1, and we can substitute in our value here. And so that what we end up with is 30.756. Now let's think about what this means. This means that our number, 5 to the 44th, is equal to 10 to the power of 30.756, or some number times 10 to the power of 30. We'll call this number A. And we know that this number A is a single-digit number, less than 10. Because if A were greater than 10, then we would end up with an exponent value here that was greater than 31. And now that we have this in exponential form, we can easily say that the number of digits in 5 to the 44 is equal to 31, because the number of digits is just found by adding 1 to the number of the exponent of 10 in exponential form.